You want to go to Mars. Maybe not literally, maybe not personally, but the idea of it is somewhere in your imagination, placed there by decades of science fiction and recent decades of genuine engineering progress and the particular human restlessness that has always pointed toward the next horizon. Mars is the conversation now. Serious people with serious resources are treating it as an engineering problem rather than a fantasy. Rockets are being built. Trajectories are being calculated. The timeline, depending on who you ask, is somewhere between 10 years and a generation away. And in the coverage of all of this, the launches, the announcements, the renderings of red dust and habitat modules and humans in spacesuits standing on an alien world, one number is mentioned more than any other: the travel time. 6 to 9 months. That is the journey. That is the obstacle. 6 to 9 months in a spacecraft, cramped and confined, and then you are there. 6 to 9 months sounds manageable. Submarines do longer. Antarctic expeditions do longer. Humans are adaptable. 6 to 9 months is an endurance problem, a psychology problem, a logistics problem. It is not a physics problem. The physics apparently is solved. The rocket goes up, follows the trajectory, arrives at Mars. Done. But let me ask you something. What is actually happening to the human body during those 6 to 9 months in a way that no amount of human adaptability, no amount of psychological resilience, no amount of careful nutrition and exercise can fully prevent? What is the spacecraft doing to the people inside it that has nothing to do with confinement or boredom or interpersonal tension? Something physical, something at the cellular level, something that begins the moment the spacecraft leaves the protection of Earth's magnetic field and does not stop until the crew lands. And why is the equation that governs this not a rocket equation, not a trajectory equation, but an equation describing the interaction between ionizing radiation and biological tissue? The most underreported number in the entire Mars program. The answer involves physics that has been known for decades, biology that has been studied on the International Space Station for 20 years, and a set of numbers that, when you put them together honestly, produce a picture of the Mars mission that the enthusiastic coverage consistently underemphasizes. The answer is going to make 6 to 9 months feel different. Now let's be fair to the optimistic framing, because it is not dishonest. Humans have survived in space for extended periods. The record for continuous spaceflight is held by Russian cosmonaut Valery Polyakov. 437 days on Mir, returned to Earth functional, walked off the landing capsule. Scott Kelly spent nearly a year on the International Space Station and was studied in extraordinary detail alongside his identical twin brother on Earth, providing the most comprehensive data set on long-duration spaceflight physiology ever collected. Astronauts return from long missions and recover. The human body is resilient. The problems are known and being worked on. This is not a showstopper. You might say, people have survived extended spaceflight. The challenges are real but manageable with proper countermeasures. The risks are accepted by the people taking them, who are professionals making informed choices. And that is a fair characterization of the current state of the conversation. Let's check what the specific numbers say about the specific threat that is hardest to engineer around. If you want to understand how the universe actually works, not just how it looks, but how it works, hit that subscribe button. We are going to take things apart and see what makes them tick. Let's find things out together. Here is the physics of the problem. Surrounding Earth, generated by its rotating iron core, is a magnetic field, the magnetosphere, that deflects the majority of the charged particles streaming from the sun and from sources beyond the solar system. The field acts like an invisible shield, bending the paths of protons and electrons and heavier ions before they reach the atmosphere and the surface. The International Space Station orbits within this shield, at an altitude of roughly 400 kilometers, inside the magnetosphere's protection. Mars has no global magnetic field. Its core cooled and solidified billions of years ago. The dynamo stopped, and the magnetic field collapsed. Mars has a thin, patchy remnant magnetism in some crustal regions, but no global protective field. The surface of Mars, and the space between Earth and Mars, is exposed directly to the full radiation environment of deep space. That radiation environment has two distinct components, and they are different threats requiring different considerations. The first is the solar wind and solar energetic particle events, streams of protons and heavier ions ejected by the sun intensified during solar flares and coronal mass ejections. These are relatively low energy, blocked effectively by modest shielding. A meter of water or polyethylene stops most of them. The threat is manageable with sufficient mass in the spacecraft walls or with a dedicated storm shelter, a heavily shielded small volume where crew can retreat during solar events. Solar energetic particle events are dangerous but addressable. The second component is the one that keeps radiation physicists awake at night: galactic cosmic rays. These are not from the sun. They come from sources distributed across the galaxy: supernova remnants, neutron stars, other energetic astrophysical objects. And they arrive from all directions, continuously, day and night, solar maximum and solar minimum, regardless of solar weather. They are extremely high energy, far higher than solar particles, and they penetrate almost everything. Here is the analogy that makes the shielding problem visceral. Imagine you are trying to stop a bullet with a sheet of paper. Adding more paper helps. 2 sheets stop more than 1. But now imagine a bullet so fast and so energetic that when it hits the paper, it does not just stop or pass through, it fragments, spraying secondary particles in all directions. More paper means more fragmentation, more secondary spray. Beyond a certain thickness, adding more shielding makes the radiation dose worse because the secondary particle shower it generates is more damaging than the original particle would have been. Galactic cosmic rays are that bullet. High Z, high energy ions, heavy nuclei like iron traveling at significant fractions of the speed of light, cannot be stopped by any shielding mass that a spacecraft could realistically carry. And when they pass through matter, they produce secondary cascades of particles. The shielding problem for galactic cosmic rays is not solved by adding mass. It requires either active magnetic shielding, generating an artificial magnetosphere around the spacecraft, which requires enormous power and has not been demonstrated at scale, or accepting the exposure. Do you see what happens? Here is what the numbers say. Radiation exposure is measured in sieverts, a unit that combines the physical dose with a weighting factor for the biological effectiveness of different radiation types. The annual limit for radiation workers in most countries is 20 millisieverts. NASA's career limit for astronauts has historically been set to correspond to a 3% increased risk of fatal cancer, which translates to different dose limits depending on age and sex, ranging from roughly 600 millisieverts for older male astronauts to roughly 170 millisieverts for younger female astronauts. Astronauts on the International Space Station receive roughly 150 to 200 millisieverts per year, already approaching or exceeding career limits for some astronauts after a single long mission, even inside Earth's magnetosphere. Outside the magnetosphere, on a transit to Mars, the dose rate is roughly 2 to 3 times higher. A 6-month transit to Mars delivers approximately 300 millisieverts in transit alone. The 6-month stay on the surface, with Mars's thin atmosphere providing minimal shielding and no global magnetic field, adds roughly another 200 millisieverts. The 6-month return adds another 300 millisieverts. A complete Mars mission, by the current best estimates from NASA radiation models and measurements taken by the Curiosity rover's radiation detector, delivers approximately 1,000 millisieverts, 1 sievert, to the crew. 1 sievert exceeds NASA's career limits for most astronaut categories. For younger female astronauts, it is approximately 6 times their career limit. For older male astronauts, it is roughly 1.5 times the career limit. And these are not worst-case estimates. These are the nominal estimates for a mission that does not encounter a major solar energetic particle event along the way. This is the part that keeps me up at night, because here is the biological reality of what that dose means, stated without softening. Ionizing radiation damages DNA. Some damage is repaired by cellular repair mechanisms, some is not. Unrepaired or misrepaired DNA damage accumulates over a lifetime and elevates cancer risk. 1 sievert of mixed radiation, including the high-energy heavy ions of galactic cosmic rays, which are particularly effective at creating dense ionization tracts through tissue, corresponds to a roughly 5% increase in lifetime cancer mortality risk, on top of the baseline risk that exists for everyone. 5% increased cancer mortality sounds manageable, until you consider that this is a single mission. that the risk is not distributed across a lifetime but delivered in concentrated form over 18 months, and that the high-energy heavy ions produce a specific type of damage, clustered DNA strand breaks along the particle track, that cellular repair mechanisms handle less effectively than the lower energy radiation that the standard risk models were calibrated on. The actual biological effectiveness of galactic cosmic ray heavy ions in human tissue is not fully characterized. The uncertainty in the risk estimate is large, and the uncertainty is not symmetric. There are plausible reasons to think the risk might be higher than the nominal models predict. Beyond cancer, the radiation environment affects the central nervous system in ways that are only beginning to be understood. Studies on rodents exposed to simulated galactic cosmic ray radiation have shown cognitive deficits, impaired memory, reduced learning ability, increased anxiety behaviors at doses relevant to Mars missions. The mechanism involves direct radiation damage to neurons and indirect inflammatory responses in brain tissue. Whether these effects occur in humans at similar doses and at what severity is not yet known. The data from astronauts returning from long ISS missions shows some cognitive effects, but ISS missions occur inside the magnetosphere at much lower galactic cosmic ray doses. What happens to human cognition during and after a Mars mission is genuinely uncertain. The people making the journey would be making it without knowing the full picture of what it is doing to their brains. Now bring this back to the equation in the title. It is not a single equation. It is a set of relationships between dose, shielding, distance, time, and biological effect that together define the radiation landscape of deep space travel. The equation is not unsolved, it is solved. The answers it produces are the numbers above. The reason those numbers have not changed the dominant narrative of Mars enthusiasm is not because they are being hidden. It is because they are being weighed against other considerations. Exploration value, long-term species survival arguments, the willing acceptance of risk by the people who will make the journey, and because the engineers are working on active shielding and pharmacological countermeasures and optimized mission trajectories that minimize time in the most dangerous radiation environments. Progress is being made, but the equation has not changed. The galactic cosmic ray flux is what it is. The cross-section of human tissue is what it is. The DNA damage mechanisms are what they are. The cancer and neurological risks are real, they are significant, and they are the price of the journey with the technology currently available. Here is what I find myself thinking when I sit with this honestly. The people who will go to Mars will know this. They will have read the numbers, consulted with radiation oncologists, weighed the risks against their reasons for going. Some risks are worth taking. Humans have always accepted risk for exploration, for discovery, for the expansion of what is possible. But the risk should be seen clearly, not managed away by optimistic framing, not buried in technical appendices. The equation that makes space travel deadly is not a footnote to the Mars program, it is one of its central facts. The journey is possible. The physics permits it. The human body can survive it, probably, in most cases, with elevated long-term risk. The stars are not safe, they never were, but they are there. And we are the kind of thing that goes anyway. If this twisted your brain a little bit, good, that means it's working. I'll see you in the next one.